Hello, my name is Kemal Analan with over 25 years of experience in the telecommunication industry. My expertise encompasses a profound knowledge of net. Tems investigation is a powerful drive testing solution for initial kernel, 2G site acceptance, software upgrade verification, new feature validation, network troubleshooting, and more. Using Tems Discovery Analytics dashboard, reports, and RF diagnostic tools, you can uncover issues affecting your subscriber faster and more easily. You will get the root cause quickly to fix the issues, and result is better subscriber experience and improve the efficiency of your network quality teams. Tems, Telecom Equipment and Monitoring System. A software tool used to monitor, analyze, and troubleshoot cellular networks, providing insights into the network, performance, coverage, and quality of service. Now we can discover for the Tems. This is for menu bar, and this is for top bar, and this is for status bar. And if the mobile and GPS is connected, we can see on the right corner. And this this is for standard bars, which is included. And this is for workspace. Let's continue overview tab. The overview tab The overview tab is Tems Telecom Equipment and Monitoring System. It is a summary module that provides a high-level view of entire drive test or data collection session. This tab presents a concise and quantitative overview of the key performance indicators, I mean KPIs, and metrics, including network coverage, signal strength, data output, and quality of service. The overview tab is designed to give users a quickly and easy to understand snapshot of the overall network performance, allowing them to rapidly identify areas of interest, detect potential issues, and prioritize further analyze and troubleshooting efforts. The information present in Overview tab is typically summarized, and the more detailed data and analysis present in other tabs, such as the map, scanner, and data tabs, providing a convenient and efficient way to get broad understanding of the network's behavior and performance. Now let's continue signaling. The signaling tab provides comprehensive display of signaling information required a fundamental understanding of OCI TCP networks models, as well as familiarity with layer 2 and layer 3 messages to access the various tables, including layer 3 and layer 2 events and model and mode reports. Users can navigate to presentation menu and select the corresponding signaling table, allowing for sequential view of each table of facility in deep analysis and troubleshooting. Now, let's continue the data. The data tab Tems Telecom Equipment and Monitoring System is a functional module that displays packet switching (PS) information which is obtained from data card or modem used during a drive test. This tab provides a comprehensive overview of data services. We can see performance allowing users to analyze and troubleshoot data-related issues such as data throughput, latency, and quality of service. The data typically includes various charts and tables that can be accessed through presentation menu, enabling users to drill down into the specific details and gain deeper understanding of data service performance. Now we can continue map. The map tab in Tems Telecom Equipment and Monitoring System is a graphical representation module that displays the geographical location of cellular network, measurements and events collection during a drive test or other data collection activities. The Map tab provides a visual interface for users to analyze and interpret the spatial distribution of network performance metrics such as coverage, signal strength, and quality of service in relation to physical environment. This tab typically integrates with mapping technology such as GIS technology, I mean Geographical Information System, to enable users to view and interact with the data in geopotential context, facilitating an identification of trends, patterns, and areas of interest for further investigation and optimization. Now we are continue for scanner. The scanner tab in Tems Telecom Equipment and Monitoring System is a module that displays real-time scanning data and information related to cellular network environments. This tab provides a comprehensive overview of scanning results, including details and available cells, signal strength, frequency, and other relevant parameters. The scanner tab is typically used to analyze and troubleshoot network issues, such as coverage gaps, interference, and handover problems, by allowing users to visualize and interpret the scanning data in a clear and concise manner. The information present in the Scanner tab can be used to identify potential users, optimize network. The control and the config, CTRL and config. It means control and config tab in Tems. Telecom Equipment and Monitoring System is a module that provides users with a centralized interface to manage and configure the system settings, parameters, and operational controls. This tab allows to users exercise control over various aspects of system, including data collection, logging, and analyzing, as well as configure system parameters such as scanning settings, measurement intervals, and alarm thresholds. The CTRL and config tab is typically used to customize system behavior, optimize the performance, ensure that it is operating in accordance with user-specific requirements and needs. Through this tab, users can also access advanced features such as scripting, automation, and integration with other systems to further enhance the system's functionality and capabilities. GSM module. All tables accessible within this workspace can be readily open it via presentation menu by navigation to GSM and select the relevant window as illustrated in the accompanying screenshots. These tables are specifically designed to support 2G derived text analysis, providing detailed insights into the key radio parameters and radio behavior, thereby facilitating comprehensive uh, evaluation and assessment. Let's continue for GSM modules. Under presentation, you can see the GSM modules. These GSM modules, under GSM modules, you can select Tems navigation path, servicing cell information, radio parameters, call status, stats, system information, so on. I can give you some information. If you want to connect all equipments, you have to click on the left corner. If you want to disconnect all equipments at the same time, you can click this one. However, if you want to connect piece of equipments, you have to use the middle of the two buttons. The first button, you can select the equipments like MS1, MS2, GPS, something like that. Then you can click here to connect or disconnect. If the upper bars is disappeared, go to the view and or layout menu to see if the measurements bars were accidentally hidden. Use the option to restore or reset the layout, bring them back. So don't worry, if you lose any bars, you can bring easily in these options. From this interface, we can determine the network to which mobile phones are currently connected. So you can see here the mobiles and status. If you want one mobile to just dedicate to work for GSM like that, then you can right click here. If you go to equipment awards, you can right click here. Then if you go to equipment awards, we can lock MS1 device to GSM only mode from this interface. If you registered your device to a single frequency, you can configure it accordingly in this interface. For example, if you want to lock a GSM phone to one specific frequency, let's say RFCN 33, you will open to device configure interface. You can see in the pictures. Open the device, configure the interface in the tabs, select the option to lock to the device to specific RFCN for RFCN 33. This ensures the phone remains on that single frequency through the test, allowing you measure its performance without interference from other channels. Ensure you have a cell file in a compatible format, typically a CSV or TXT file. The file should contain column for cell ID, latitude, longitude, frequency, and other relevant parameters. Import the cell file. In the general configuration, go to configuration under general. You can open these windows. In the general configuration window, look the cell file lock option. this option. Click on it and access the settings. Access the settings related to SAL-file login. Navigate the location of your computer and select it. Configure the SAL file. After selection the file, a dialog box may appear asking you to map the columns in your SAL file to the corresponding files in Tems. Make sure to match columns correctly and cell ID, latitude, longitude, frequency. Everything will be okay. After that, click OK and import to load the SAL file into the Tems. In Tems investigation, Teams and color coding setting allow you to customize the look and feel of various measurements, windows, maps, and panels, while the exact step and option may vary depending on your Tems version. How do themes or color schemas typically work and how you might configure them? The first way, accessing theme or layout settings. Go to the View or Tools menu and look for Layout option or settings. Some versions provide the dedicated themes and color settings tab, while others have disintegrate into the layout. What can be customized? We can customize map view colors. You can define how cells, routes, and coverage are displayed on the map. For example, cell might be shown different color depending on the technology, 2G, 3G, 4G, 5G, or coverage areas. The second is measurement windows. The bars or panels showing RF parameters, RX, such as RX level, RX coil, RS, RP, etc., can often be color coded. You can set color threshold to quickly identify good, fair, poor signal, something like that. The other event indicators. Specific events like call drop, handovers, or attach failures may be highlighted in different colors to draw attention in real time in post-processing logs. Common usage example. Coverage threshold define a color scale for signal spread. For example, green for strong coverage, yellow is for moderate, and red is for weak. This helps you instantly see coverage quickly in drive test. Technology layers assign distinct colors. Customer layouts for reporting. Create specific color-coded layouts, for example, for an executive summary that highlighted only critical metrics, like drop calls or low throughput zones. Sample steps to adjustment. Tab theme color may vary version. You can open Tools option or View Layout. Then locate the theme color or approach the section. Select predefinition theme if able or adjustment color. Then save your settings under custom name so you can load them features. Tips for effective use. Keep color schemas simple and intuitive. For example, green is good, red is bad. Documented or label your custom color settings so team member can easily understand them. Regularly update your color threshold if network condition or test strategies changes. By configuring the theme and color settings, you can quickly identify problems area and present drive test result or live measurements in a clear visual appealing format. This visual clarify it is especially helpful during optimization and troubleshooting. as it allows you and your team to pinpoint issues more efficiently. Current channel. Current channel. You can see here. There is a time. Time show the current computer system time. Cell name. A unique identifier that shows which sector cell is currently serving the mobile service as defined in the Tems cell file database, representing the physical location and coverage area of specific base station sector. CGI cell global identify. A standardization unique identification code for cellular network sector combining MCC, MNC, LAC, and cell ID. Components which provides a global district address for each cell sector in mobile networks. Cell GPRS support. A binary yes or no indicator that shows whether a cell sector support GPRS, I mean General Packet Radio Service, data transmission capabilities. Band. The operating frequency range of the mobile network, for example GSM 900, 1800, something like that, indicates which radio spectrum is being used for communication between the mobile device and base station. BCCH RFCN, the specific radio frequency channel number used by the base station to broadcast control information and system parameters. Parameters to mobile device for cell selection and network access. TCH RFCN. The specific radio frequency channel number assigned for carrying active voice data traffic between the mobile device and base station during a call. Basic. A unique identifier code combining network color code NCC and base station color code BCC, ranging from 0 to 7, each used to distinguish between neighbor cells and prevent interference during network synchronization. Mode. The current operation state of the mobile device, indicating whether it is the idle standby dedicated voice circuit switch data or packet GPRS data mode. Time slot. A specific segment of time within the TDMA, I mean time division multiply access frame assigned to mobile device for communication numbered 0 to 7 to used resource allocation GSM networks. Channel type indicates the specific categories of logical channel being used, like SSH, TCH, full rate, TCH half rate, BCCH, etc. for communication between mobile device and network. Channel mode. Specifies the current transmission mode of channel, such as signaling, speech data, and its configuration for handling different types of traffic. Ciphering algorithms. The encryption methods A5 over 1, A5 over 2, or A5 over 3 used to secure the communication between the mobile device and networks. Subchannel numbers. The specification identifier for the subdivision of main channel used for resource allocation and traffic management. Traffic traffic uh, the specific identifier for subdivision of main channel used to resource allocation and traffic management within the GSM frame structure. Hopping channel. A channel that dynamically switch between different frequency during the transmission for reduce interference and improve signal quality. Hopping frequency. The set of predefined radio frequency that a channel uses during frequency hopping to enhance communication reliability. Mobile allocation index offset (MIO). An offset number of assigned to each mobile device that determines its starting point in the frequency hopping sequence. Hopping sequence number HSN. A number 0 to 63 that defines the specific pattern or sequence of frequency channel used during the frequency hopping operation. First, frame ensure rate. The percentage of voice data frame discarded due to uncorrectable errors measurement as the ratio of drops frames to total receive frames with ideal range of 0 to 4%. Concentrate good. Fair actual. Fair actual. Frame ensure rate actual. The real time measurement of drop frames to total received frames showing current frame loss ratio with ranges 0 to 4% is good. 4 and 15% is degraded. More than 15 is unnecessary. Bare actual bit error rate. The real-time bit ratio of incorrect bits to total transmission to total transmitted bits measurement current transmission quality and directly influencing RX value in voice communication. CQI. CQI means speech quality index, a sophisticated measurement updated every 0.5 seconds that reflects speech quality based on bare and fair calculation with good ranges beginning 18 to 30. CI carrier and interference. The ratio between the desired carrier signal strength and unwanted interference signaling, indicating the quality and quality of radio connection. MS power MS power control level. The current transmission power level of mobile station automatically adjusted based on distance and signal condition, optimize battery life and minimize interference. DTX. DTX means discontinuous transmission, a power-saving feature that stops transmission during the speech pause, reducing interference and battery consumption. Timing advance. TA. A value is 0 to 63 indicated distance between mobile to station and base station, where each unit represents approximately 550 meters. Radio link timeout counter. Current. The current value of radio link counter tracking connection quality before potential discounting. Radio link time out counter max. The maximum allowed value 4 to 64 in step 4 for radio link failures before forced discounting, typically set as 16, 20, 25, something like that. MS beware modified. The current configuration status of mobile station showing enable or disable features like handover and multi-band reporting capabilities. RX quality. Definition average receive signal quality measurement on the time slot based on bit error rate. The threshold is RX 0 bit error rate 0.2 less than 0.2 is excellent. RX 1 0.2 between 0.2 0.4 it's very good. RX coil 0.4 to 0.8 is good. RX coil 0.8 to 1.6 percentage is moderate. RX coil 1.6 to 3.2 is fair. RX coil 3.2 to 6.4 is poor. RX coil 4 to 12.8 is fair poor. RX coil 7 more than 12.8 is extremely poor. Use the measurement voice quality important threshold for calls without frequency hopping should be less than 4. For calls with frequency hopping should be less than 5. Value is 0 to 3, generally acceptable good. Value is 4, between 4 to 7 is indicate degraded service quality. You can see in the pictures, you can analyze. RX level. Service signal level. Definition average receive signal strength. Serving cell measurement on all the time slot. RX level full for full rate traffic channel. RX level sub use the DTX DL is activate in network. Range is -10 to 65 dBm is very good. -65 to -75 dBm is good. -75 to -95 dBm is fair. -95 to -105 dBm is worst. Servicing and neighbors. Sun name, you can see here the identifier of neighbor cells as defined in Tems cell file, showing potential handover candidates around the serving cell. You can see all these neighbors and others. RFCN, this one. Frequency channel numbers. Absolutely radio frequency channel numbers. The specific frequency channel number used by neighboring cells for their broadcast control channel, BCCH. You can see this cell is RFCN 614. RX level, this one. The measurement signal strength of neighboring cell in dBm used to evaluate potential handovers. This cell RFCN 64, and the RX level, as before explained, RX level minus 53. It's good. And C1 and C2 parameters. This one C1 and C2 parameters. Cell selection, reselection parameters, where C1 is path loss criteria and C2 is the reselection criteria used to evaluate cell suitable. C31 and C32 hierarchical cell structure parameters used in the cell reselection decision when the hierarchical and cell structures are implemented in the network. So we will see this cell RFCN base station identify code as we before explained, NCC plus BCC and RX level. If there is a border site or something like that, we will see C1, C2, the other C parameters. Adjacent channel signal strength. The measurement signals power from neighboring frequency channel that could potentially cause interference with main servicing channel. Carrier interference ratio, CI. The radio between desired carrier signal strength and unwanted interference signal measurement in dBm, indicating inequality clarify of radio connection. In Tems investigation, the frequency scan feature lets you measure and visualize the signal levels across a specified range of frequencies or channels without being restricted to single serving cell. This helps identify potential interference source, determine available carriers or detect coverage gaps, although the exact step may vary by times. Let's overview scan. Purpose of frequency scanning. Identify available frequency, pinpoint which frequency or channel, for example RFCN, ERFCN, etc., or actively used in the environment. Measurement signal strength. Determine how strong each frequency is potential revealing interference or high noise channels. Spectrum analyzing. View a graph or table of frequency power useful for planning new sites, analyzing interference or verifying coverage. Configuration a frequency scan. First, select scan mode or device. In the device or scan setting menu, choose a support phone or scanning receiver capability of frequency scanning. Some devices may allow scanning only in certain bands, for example GSM 900 or LT band. Define frequency range or channel list. This is second issue. Special start and end frequency, for example 935, 960 MHz for GSM 900 downlink, or input list of frequency channels RFCN. Depending on the network technology, you can set the bandwidth or spacing between channels to scan. The third issue, adjust granularity and sweep time. Set how many points or channels per megahertz you want to measure and the scan speed. Higher granularity can give more details, but takes longer. Start the scan. Begin the scan and Tems will measure receive power for each frequency or channel across the defined range. View and interpreting result. Real-time or post-processing data during or after the scan, you can view the graphical display, frequency, receive power, or numeric table of each channel and signal level. Identify peaks. Look for spikes in the graphs where strong signal appear. This might corresponding for active carriers or source of interference. Generating reports. Export the result to CSV, PDF, or other formats for further analyzing and documentation. Example scenario. Suppose you want to check GSM 900 downing band 935, 960 MHz to see which frequency local operators are using and measure interference level. In Tems, connect the device and support scanning mode, some scanner phones, or dedicated scanner units. Go to the frequency scan configuration and set the start frequency to 935 MHz and the end frequency is 960 MHz. Choose an appropriate resolution, 200 kHz, for example, step, for depending on your goals. Initiate the scan and let them sweep through the selected range. Once the scan completed, analyze the display and spectrum graph and see which frequency have high power level. You may notice strong peak frequency that local operators use the GSM 900. Save the export and scan data for further examination for reporting. Tips and best practice. Use the dedicated scanner when possible. Scanning receiving often provides wider bandwidth and more accurate result than standard mobile device. Correlate with other measurements. Combine frequency scan data with drive test logs or site data. Understand how found frequency align with no operator channels. Rerun scans at different location times. By sampling multiple areas or conducting scan at various times, you can observe variation in interference or operator usage. By performing detailed frequency scan in Tems, you gain a clear picture of network usage and potential interference sources. This information is invaluable for network planning, optimization, and troubleshooting. In DSM network, a mobile phone or data device typically needs a minimum signal strength and corresponding signal quality to maintain reliable communication. Bad quality due to low signal strength arises when the receive power from the serving cell is insufficient for clear voice calls or robust and throughput. Below are some common reasons and reminders. Distance from the cell site. The further you move from a base station (BTS), the weaker the receive signal becomes. In large cells or rural areas, coverage is often designed to be more spread out in signal strength, maybe low, far from the towers. Physical obstruction. Wood hills, dense foliage, and other obstacles can scientifically weaken the radio signal, leading to poor quality indoors or urban canyons. High-rise buildings can cause reflection, diffraction, or blocking of signal, further reducing effective coverage. Poor cell selection or overshooting. Overshooting cells that serve users who are actually farther away than optimum can lead to poor signal strength at the user site. If the network parameters such as neighbor list and handover margin are not optimized, mobile may stay on distance cell instead of hanging over to closer one, causing low signal strength. Influence power for antenna configuration. If the BTS transmit power is too low or if the antenna teeth is too downward, coverage might not reach the intended area. Suboptimal antenna selection gain bandwidth or incorrect orientation can also weaken signal strength, RF interference, and quality degradation. In addition to absolute signal power, interference from neighboring cell or external source, other wireless system can reduce signal quality, often referred to as low SNR, signal to interference plus noise ratio. How to improve addresses low signal strength? Network optimization adjust antenna tilt height and azimuth to better match the coverage needs. Fine-tune transmit power to ensure adequate coverage without creating excessive interference. Optimize cell selection handover parameters so users connect to the closest or strongest cell. Repeaters small cell. In area with presently weak coverage, deploy signal boosters, repeaters, or small cell, micro, pico, femto cell to enhance indoor or localization coverage. Infrastructure upgrades, where feasible at new site or sectorize existing cell to reduce coverage gaps and improve signal strength across the network. Device side solution. User can switch to devices with better RF performance or external antenna connection if the coverage is poor in indoor or in remote area. By tracking the root causes, whether it is distance from the site, physical obstruction, suboptimal cell planning, or interference, operators can mitigate low signal strength issues, yielding better call quality, fewer drops call, and improved data throughput. In GSM network, a mobile phone or data device typically needs a minimum signal strength and corresponding signal quality to maintain reliable communication. Bad quality due to low signal strength areas. When this received power from the servicing cell is insufficient for the clear voice call or robust data throughput below area. Some common reason and remedies. Distance from the cell site. The farther you move from a base station (BTS), the weaker the receiver signal become. In larger cell or rural area, coverage is often designed to be more spread out to signal strength, maybe low far from the towers. Physical obstruction, building hills, dance, foliage, and other obstacles can significantly weaken the radio signal, leading to poor quality indoors or urban canyon. High-rise buildings can cause reflection, diffraction, or blocking of signal, further reducing effective coverage. Poor cell selection or overshooting. Overshooting cells that serve users who are actually farther away from optimum can lead to poor signal strength and the user side. If the network parameters such as neighbor list or handover margin are not optimized, a mobile may stay in a distant cell instead of hanging over a closer one, causing low signal strength. In insufficient power and antenna configuration. If BTS transmit power is too low or the antenna tilt too downward, coverage might be not reached to intended area. Suboptimal antenna selection in bandwidth or incorrection oriented can also weaken signal strength. RF interference and quality degradation. In addition to absolute signal power interference can neighboring cell or external sources. Other wireless system can reduce signal quality, often referred to as low SNR, signal to interference noise radio. Causes of overshooting: high antenna placement at tall tower or An antenna oriented at a low tilt can radiate signal over larger distance. Exercise transmit power. If the BTS power is set too high, the coverage footprint can expand it beyond the planet region. Favorable propagation condition. In certain environments, in floods, open terrain, over water, etc., radio signal can travel further with less attenuation. The second is problem caused by overshooting, interference and reduced quality, servicing mobile device far from cells center and degrading network quality and add interference for neighboring cells. In efficiency, resource quality, distance mobile may struggle to maintain to reliable uplink due to limited power on the handset, creating poor power channel quality and drop calls. Handover issues. If a problem device unexpected latches onto the faraway overshooting cell, it may experience frequently handovers or fail to hand over to near to cell, causing call drop or reduced throughput. Mitigation techniques adjust antenna tilt in introduction. Mechanical or electrical down tilt can help reduce the distance, the main lobe of the signal travel. Optimizing transmit power. Fine tuning in the output power at the BTS helps keep coverage contained with the intended area. Reviewing antenna patterns, selecting an antenna with an appropriate beam width and gain can ensure more controlled coverage. Neighbor list planning. Proper cell neighbor planning and handover parameter settings, power control, handover margin help minimize the negative effect or overshooting on handovers. You can see in the pictures this cell is this cell is overshooting in this area, and this may interfere in that placement. In GSM network, interference refers to any unwanted signal or noise that degrade to quality of the desired GSM carrier. Signal interference can come from various sources, other GSM cells using same or neighboring frequencies, other wireless system or external equipment emitting radio frequencies. When the interference is present, users may experience lower quality, reduced data throughput, more drop calls, and lower overall network capacity. Key type of interference in GSM. So we can explain to this. Co-channel interference occurs when two or more GSM cells are the same frequency channel because GSM networks often reuse frequency to maximize efficiency. Careful planning and power control are essential to limited co-channel interference. Adjacent channel interference happens when the signal from neighboring channel overlap and affect the adjacent frequency. This may exacerbate by high transmit power or poor filtering. External interference. Non-GSM device, illegal repeaters or industrial equipment can create noise or GSM bands distributing service. Operating mitigate GSM interference by selecting appropriate frequency reuse pattern, optimizing power levels, adjusting antenna tilts, and performing ongoing drive tests or frequency scan to identify any resolved interference resource. In Tems for GSM network, interference is typically discovered by analyzing measurement data, either from drive test logs or frequency scan to detect abnormal signal pattern or poor signal quality. Here is how you might identify interference in GSM settings. First, drive test measurement in call. During a GSM call test, Tems display key parameters like RX level, signal strength, RX quality, signal quality, and event message. If RX level is sufficiently high, but RX quality is consistently poor, RX quality, for example, between 4 to 7, is suggests to interference is decreasing quality rather than low signal. Repeated handover or call drops in area with otherwise strong coverage can also be a sign of interference. Frequency scan for GSM configure times to scan to GSM band of interest. For example, GSM 900, TCS 1800 for downlink frequency. RFCN observe the power level across all channels. A channel showing unusual, high noisy, or unexplained peaks may indicate interference overlapping carriers. Example scenario: suspecting external interference GSM 900 in Tems set up frequency scan from 935 to 960 MHz. Typically GSM downlink band. Let the scanner sweep through all RFCN this range. Examine and resulting spectrum graph. If any RFCN other than the no carriers shown abnormally high power, or if the noise floor is elevated, this may indicate interference cross interference with your operator's frequency. Plan to ensure that no legitimate carrier are transmitting on that channel. B. Drive test log analyze. Construct a drive test forcing the mobile to stay on specific channel if feasible, or just letting it camp on the best cell after collection data. Review areas with high RX level but poor RX quality. Check the layer 3 message for the frequently handover attempts for TCH. Reassignment which could point to interference impact. Mitigation next step. If you detect interference on a certain channel, verify whether it's belong to your own network or neighboring operators. You may need to adjust your frequency plan and or coordinate with external parties. If it is an unlicensed signal, adjust parameters like transmit power, antenna tilt, or neighbor definition to reduce effect co-channel or adjacent channel interference. If external equipment is cause noise, it may require location and removing that source by integrating frequency scan, drive test analyze. And knowledge of your network's channel assign, you can pinpoint and address interference in GSM network using Tems. Handover problem in GSM. If you observe any handover issues, first verify that all handover related parameters are correctly configured to avoid illogical handovers. Keep in mind that there is always a risk creating handover loops if parameters between neighboring cell or not set properly. Let's continue late handovers. In some situations, you may notice that the handover process occurred later than expected. Several factors can cause this delay. First, verify that the BCH basic of the target of cell is being decoded properly. You can confirm this by checking the measurement report (MR) from layer 3 message Tems. You should also consult statistical data, review the handover margin between neighboring cells. If the margin for level, quality, or power budget-based handover are not configured correctly, the handover may not take place at the right time. Specification: if these margins are too large, the handover will be delayed. This condition is often, generally. Call dinging in GSM and other cellular network occurs when a mobile device remains connected to serving cell that has become suboptimal even through a better cell, stronger or higher quality signal is available. Essentially, the call is dragged for too long on the originated cell instead of being handed over in timely manner. Below are the main points. The first is definition and symptoms. A user moves away from the serving cell coverage area, yet the mobile station continues to use the same cell instead of handing over to nearer one. The call experience. Deteriorating signal strength or quality leading to potential call drops or poor user experience. Second is common causes. Improve handover parameters. If handover threshold or hysteresis value are set too high, the network delays handing the user of the better side. Mismatch or missing neighbor relation can also lead to delay or failed handovers. The second is coverage overlap and overshooting. A cell may overshoot beyond its intended coverage area, causing device to remain compact on it rather than switching to closer cell. Network condition purity. If the target cell is frequently congested or has resource limitation, the networks may delay handover, resulting in call dragging. Consequence: dragged call quality and increased likelihood of drop calls. Users dissatisfied due to poor voice quality or slower data rate. Impact on network KPIs, key performance indicators, such as lower handover success rates and higher drop call rates. Mitigation strategies, parameter optimization, lower hysteresis or tighten threshold RX double RX coil so that phone hands over more promptly to better cell. Review neighbor list to ensure correct intra or inter-cell handover relationship. Coverage planning and tuning. Adjust antenna tilt oriented or transmitted power or reduce overshoot and reinforce coverage in this desired area. Sectorize cells and add new sites to reduce overlap and provide stronger coverage where needed. Load balancing measurements. Implemented features that distribute traffic more evenly among available cells prevents one cell from becoming a lock-in due to congestion or configuration. Regular drive testing and optimization. Use drive test data and performance statistics in identify to cell with call dragging issues that tune parameter to improve handover performance. By carefully configuration neighbor list, handover threshold, and antenna parameters, operators can minimize call dragging, ensure smoother handover, and provide better overall user experience in GSM networks. Ping-pong handover. Hysteresis is used to prevent the ping-pong effect, which is characterized by mobile station making multiple consecutive handovers between two cells in quick succession. This phenomenon can be triggered by feeding the mobile station moving in a zigzag path reception of similar signal levels from multiple servers, or the absence of dominant server. If measurement analysis reveals mismatch in parameter settings, you can adjust the hysteresis and offset parameters to help reduce ping-pong handover. Similarly, incorrect handover margin can also cause frequently ping-pong handovers. Therefore, this margin must be set probably to probably so that handovers occur at the right time. In GSM and other cellular networks, no dominant server uh, refers to coverage situation in which the mobile device does not detect a single cell server. That clearly provides the strongest signal compared and the neighbor cells. Instead, multiple cells may have regularly the same signal strength and quality, or the serving cell signal may fluctuate rapidly, preventing the device from settling on the stable server. Key causes. The first is coverage overlap. In dense urban environments or location where the cells have overlapping coverage with similar power levels, in device may see several cells with compressible signal strength. This overlap results in margin difference in downlink power levels, making it hard for the device lock onto a single best cell, RF interference and multiband. Reflection from buildings, uh, terrain, and other structure can create multipath affected causes rapidly fluctuation in received signal levels. When the signal's quality or its quality is inconsistent, the network may frequently re-evaluate handover or cell reselection, mainly no stable dominant cell. Antenna configuration or overshooting. If multiple cells have antennas with similar tilt, height, and transmit power, their coverage footprint may largely overlap, or shooting cell can serve users who are equally close or closer to another BTS, contributing to confusing about which cell is best. Impact on network and user experience. Frequently, ping-pong handovers can occur cause the phone sees multiple equally strong cells and continuously switches between them. Increased signaling load the network, which can reduce over efficiency, potentially for degraded call quality or drop calls if handovers are not well turned. Reduced data throughput due to increasing overhead and shifting among cells. Migration strategies, coverage, and capacity planning. Adjust antenna teeth power or azimuth to ensure one cell is clearly stronger in each geographical area. Sectorize cell more effectively or add new sites to reduce overlap and provide clearly dominant coverage. Neighbor list and handover parameter optimization. Fine-tune handover threshold, hysteresis, and offset parameters to avoid frequent cell changes. Ensure accurate and current neighbor list so that phones can evaluate correct candidate cells, avoiding confusion with too many options. Antenna selection. Use antenna with appropriate beam width and pattern designed to reduce unintended overlap. Optimize mechanical or electrical downtilt to focus signal where it actually needs. Use the advantage feature. Implemented load balancing coverage, shaping or power control features in modern GSM, HUMTS LT network, or further optimize how to sell overlapping and subscriber by reducing excessive overlap and ensuring that one cell is consistently stronger in given area. Operators can establish a reliable dominant server for device. This leads to fewer handovers, less interference, improved call continuity, and better overall user experience. Unnecessary handovers. Just like ping-pong handovers, incorrect margin can lead to unnecessary handovers that directly affect network performance. The more frequent these handovers, the higher the risk of quality issues and even dropped costs. Overshooting cells are one of the main contributors to these illogical handovers. Missing neighbor relation. If the best adjacent cell does not appear in the neighbor list, it suggests missing neighbor relation. As a result, the call will be handed over to whichever neighbor is currently reported as the best, which may not be truly optimal cell. I mean, the car is goes to this route, for example, and this cell is covering for the yellow yellow one, and this site is covering for purple, and this site is covering for the green placement. When the mobile is goes to this through on this way, it checking the best neighbors list. But in that list, sometimes in the BSC site, they didn't define on this site to this site as a neighbor. You can see the neighbor here also line chart. Okay, then it should be hand over this yellow to purple, but there is no neighbor relation between this cell. But this cell is neighbor to green one. So when the car goes on, and if the yellow has coverage until the green placement, then it will hand over to green. So it is not optimal, and it is not a good way to us. Fake handovers. Occasionally, you might identify a neighboring cell with excellent signal level in the neighbor list. Yet the handover attempts fail, causing the call drop despite appearing as a valid neighbor. This cell is actually not one. The confusion arises because the serving cell has not another neighbor defined with the same BSH. Always ensure that no two neighbors are configured with the same BSH for the same source cell. BSH missing from serving cell and BSH list. In some cases, you may notice that handover does not occur even though the two cells are defined as neighbors. If the neighbor's BSH number is missing from the serving cell and BSH number list, the mobile station MS will not monitor or reporting neighbor's BSH frequency, preventing any handover attempts to that cell. NCC missing from servicing cell, NCC perm list. If the neighbor's NCC network color code is not included in the serving cell NCC permit list in the mobile station, MS will not be allowed to include that neighbors in its measurement reports. No handovers attempt will be made to that cell. The same BSH and BSIG combined. The same BSIG and BSH combination during calls, the mobile station MS reports the BSH, BSIG and signal strength of the 6 strong neighbor cells to the BSC. The BSC then maps each neighbor's BSH and BSIG combination to its cell global identifier CGI. Therefore, all neighbors of signal cell must have unequivocal BSH and BSIG combination.